Hi guys, Mr Cox, Allworth again. Today we're going to do a quick video all about the alkali metals, which is a big topic that comes up in C1. So in particular we are going to look at what are the properties of alkali metals, how they're different to regular metals that we sort of see day to day, how do they react with oxygen, how do they react with anything from group 7, and the most important one, how do they react with water. So we'll have a start with the properties. What are these metals like? Okay, so here we have our top 3 of our alkali metals. So going down the group, lithium, sodium, potassium. So they are all metals just like any other metal. So lots of the properties they have would be similar. So they do conduct electricity like any metal would. However, they are a bit weird as well. So first of all, if not sure how clearly you'll see this, but they're kept in oil. They need to be kept in oil because they will react with the water and the oxygen environment around them. The other thing you might notice a bit odd is they are floating in the oil, so therefore compared to most metals they've got quite low density. Other things that are unusual, I've got a sample here of sodium, so the middle one. So you can see the colour of sodium, it's probably not very clear. It's kind of silvery, but it looks a bit sort of greyish, a bit tarnished, so it's not shiny like you'd expect a metal to be. However, second odd thing about it, they're very soft. So with very little difficulty I can cut that open, and when you do cut it open, for a very short period of time, you do get a nice shiny surface, just like you would with any other metals. They have a lot of properties in common with normal metals, but they do have some that are different, namely low density, and they're much softer. Okay, so we're going to now take these 3 metals and we are going to do some reactions with them. But before we do that, we're going to very quickly talk through what we might expect to see in some different reactions of these metals. Okay, so before we actually do any of the practicals, I just want to sort of set up and show you the basics of the equations. So, first one, we sort of know this from key history anyway. Take any metal and oxygen and you're going to make a good old metal oxide. And exactly is true for group 1, it's just the same. So for example, if you took lithium, reacted with oxygen, you would make lithium oxide. It would just be a very exciting reaction because group 1 metals are all very reactive. There is a little bit of a caveat with that some of these oxides are either peroxides or superoxides, but that's a lot more complicated and we're not going to worry about that for the purpose of this video. Second reaction, if you take a metal and react it with a halogen, if you remember a halogen is just an element from group 7, you get what is called a metal halide. So just like when you turn an element into a compound normally, you have to change the ending, halogen becomes halide. So a nice example there. If you took good old sodium, group 1 alkali metal, react with chlorine in group 7, you'd make your table salt, sodium chloride. Again, the ending now goes from ine to the ide. And for this one, I'll give you a little simple equation. You might have already noticed that it's not complete, of course. So we've got sodium plus chlorine. Chlorine lets go around as 2 atoms bonded together. You make sodium chloride. Obviously, that does need a quick bit of balancing. So 2 chlorines, you need a 2 to make 2 chlorines. That gives us 2 sodiums. So we need a 2 there as well. Okay, so those reactions are much simpler and they kind of fit with the pattern we're used to. Effectively, one thing reacts with something else and combine it to make a separate chemical. Our third one is a little bit more complicated, and these are the reactions that you really need to remember, and they're the ones we're going to do. So if you take an alkali metal and water, what do we make? Because of course most metals don't react with water, alkali metals do very easily. So let's have a go and let's see what evidence we can find. Okay guys, so we are now going to react the alkali metals, or the first 3 of them, with water. So, big bowl of water, here it is. We are going to add some good old, can you see that? Universal indicator, which is of course our indicator for acid or alkali, what the pH is. So, probably far more in there than I need. Can you see though it has gone, let's put a bit more, make it really obvious for the camera. Can you see it's got a bit of a green colour, which is what you would expect because the tap water is going to be pretty close to pH 7, so it's neutral. In fact, I'm going to put even a little bit more in just to make it really obvious. Okay, brilliant. So I've now got my 3 alkali metals and I have prepped them, so I'm not sure how clearly you'll see that. So the darkest one is my lithium samples, then my sodium, and then my potassium. Okay, so what we do, we will put them in and we'll see what evidence we can gather about what might be going on in these reactions. So, the first one. Right, so samples of lithium, in they go. Oh, doesn't want to come off. Okay, let's just pour them in. You might be able to hear their fizzing, and hopefully you will see a change in colour going on in the universal indicator. And one more bit of evidence, if I put a bit of flame to them and we're really quiet, you might hear a little pop, and you'll certainly see a flame. And if you see, the flame is a lovely red colour, just over here. It's a nice red one. Okay, so let's have a look what evidence we've gathered. Clearly, it's gone purple. Universal indicator goes purple in the presence of alkali, so hydroxide. So whatever chemical we made is called something hydroxide. We also were producing, if you heard that fizzing, we were making a gas, and that gas was flammable. So we need something that's got a hydroxide and something we've made a flammable gas. That's quite a lot of clues about what we've made. We will then just do the other chemicals so we can compare the reactivities. So if we do the same with our sodium, so in they go. Right, they're fizzing a lot more, they're moving a lot quicker, and if I put the flame to them again, you get a little pop. And they have, you probably can't see this on the video, but they have a very, very orange flame. Oh, and they're still fizzing about. Okay, our last one then. If we compare that to the lithium, these were definitely a bit faster moving. Okay, our final one, potassium. Now, you might notice for this one, I definitely didn't need a flame, they lit all on their own. Therefore, probably a lot more reactive again. Turning the universal indicator purple, and they burnt with a lovely purple flame, but there was definitely clearly there a gas that was flammable. Right, now what we need to do is see if we can take the evidence and use that to build an equation of what really happened in these reactions. Right, back at my board. So, let's have a look what we thought already. We know we put an alkali metals in fact we did 3 different ones, and we're actually with water. We're going to just home in on the potassium one because where they're all in the same group, of course, the reactions are all very similar. So, potassium was the most exciting one. That was the one that was had the purple flame in itself, lit all of its own. Potassium plus water, what do we know? We were making a gas that was flammable. Now, I've already put in here the beginning of my symbol equation because that'll help me, because our good old basic rule of chemistry, you can only make things from the atoms you start with. So if I look at this, a flammable gas, I've only got potassium, hydrogen or oxygen atoms to go with. The flammable gas I made was hydrogen. Yeah, and if you heard on the video the pop, that is the test for hydrogen gas. So we know we made some hydrogen gas. So over here, hydrogen gas is H2, and in our word equation, we will write hydrogen. In fact, we'll put it in all the places. Top one here is just our general equation. Okay, so we also know it turned the water with universal indicator a purple colour. That means you're making an alkali, and in chemistry, an alkali is a hydroxide. So we had a chemical that finishes in OH, or as words, it finishes in the word hydroxide. Now, effectively we know that's only part of the chemical because the hydroxide is always stuck to something else. It's usually stuck to a metal. In this case, what's the only metal I've got? Of course, it's the potassium. So the chemical I was making was KOH in that case, potassium hydroxide. Potassium hydroxide, and in my general equation, I'm just going to put a metal hydroxide. Because it could be any of the alkali metals. It could have been lithium, it could have been sodium, it could be potassium, or it could have been the ones below, like rubidium or cesium. Okay, we then look at that. Looks almost right. Remember though, we have to have all our symbol equations balanced. So let's quickly balance them. And this is a classic one that comes up in GCSE exams. So if we look over here, where's our problems? So hydrogen, we've got 1, 2, 3 on this side, but only 2 on this side. So logically, we must have some more hydrogen. So if I put myself a 2 there, that gives me my extra hydrogen. Okay, so that gives me 4 on this side, but only 2 on this side. So 2, 4, this side needs 4, a 2 there, that gives me 4 hydrogen on both sides. 2 oxygen on this side, that now matches the 2 oxygen on this side. 2 potassium, I therefore just need a 2 there. 2 potassium, 4 hydrogen, 2 oxygen, and 2 oxygen. And that is our balance symbol equation for the alkali metals, and of course all the rest was balanced in exactly the same way. We have one more thing to do, and that's to explain why was it that potassium was really exciting, whereas the lithium was much less so. We're going to look at an electron diagram to see if we can work out why that is the case by looking at what the atom looks like. So here are some diagrams I prepared earlier. So what we've got here, lithium, and I've just shown this what's called an electron configuration diagram, which hopefully you know. I'm literally just showing how the electrons are laid out. So I haven't shown any of the nucleus. Lithium, it's just got the 3 electrons. So the inner shell has 2 and the outer shell has 1. That's of course why they're in group 1 electron in the outer shell. Sodium, similarities. Obviously it's got 1 in the outer shell, it's in the same group. This one has 11 electrons, so 2 on the inner, then a full shell of 8, and then an outer shell again with just 1 in it. So why does this make sodium more reactive than lithium? You basically have to think, what is it that these atoms are trying to do when they react? So these metals are not very stable. The reason being, they've not got a full outer shell. They are desperately trying to lose the outer electron. When they do that, they become what we call an ion, which is a word you should know. It's a charged particle, because if they lose that 1 electron, they'll be left with 1 more proton than electron, therefore they'll have a charge of +1. So both of these are desperate to become a +1 ion, and they're going to do that by losing the outer electron. Now we're going to think, what's keeping that electron where it is? So if you remember, the nucleus, the atom in the middle, is incredibly positive, because that's where all the protons are. The electrons are negative, and it's that electrostatic force, the attraction between a plus and a minus, which is holding them in place. Now from my diagram, the clear obvious difference is sodium is much bigger because it's got an extra shell. Therefore the distance between the nucleus and the outer electron is much further away. Why does that matter? Because when this reacts, it can't just lose the electron on its own, it's got to give it to something else. In this reaction, obviously it's reacting with the water, and we're making lithium hydroxide, and we're making our hydrogen gas. In order to lose that electron, basically it's got to be pulled away by another atom. In this case, with lithium, because the distance is quite small, that attraction is still quite strong, and it's harder for that electron to be lost. Sodium, the outer electron is further than the nucleus, it's easier for that electron to be lost, and therefore it does it more readily, and the reaction is faster and more vigorous. If you were to draw potassium, it'll be bigger again, and therefore more reactive, and so on down the group. And that's why in alkali metals they get more reactive as you go down the group. I will therefore be setting you perhaps an exam question about this, because this does make a classic 6 marker. In many years they've had a question about why is it that the alkali metals get more reactive going down the group, or you could have the opposite question about group 7, why is the pattern the other way round? So be looking forward to doing that work for you guys. Thank you very much.